Welcome back to the chemical reactions series of PowerPoint presentations from Mr. Voigt's physical science class. We're dealing now with the topic of law of conservation of mass. We have recently completed labs on this topic. Our first was the conservation of mass lab, and the second was the finding a balance lab. The conservation of mass lab should have indicated for us that whatever we start with in an equation, which is the reactants, has to also be the same as the products. We learned that the mass of the glass bottle was the same before the reaction and after the reaction, which goes to show us that the same number and types of atoms on the reactant side of the equation must also be the same as on the right side of the equation, the product side. The finding a balance lab helped us practice and see that the number and types of atoms are the same. And so now we're going to take a little bit closer look on the conservation of mass topic. The law of conservation of mass says that matter can neither be created nor destroyed in an ordinary chemical reaction. In other words, whatever we start with has to be there in the end. It might look differently, but it's still there somewhere. We must account for that in our chemical equations. Chemical equations must be balanced to indicate the law of conservation of mass. Now, what does this mean? This means that the same number and types of atoms has to be the same on both the reactant and product side. So let's take a look at balancing equations. What are the tricks? Now, how do we do it? We're going to first count the number of each type of atoms on both sides. And if they match, then our equation is already balanced. And if it's not matched, then we have to balance it. We're going to start with one atom that needs balancing and write the correct coefficient in front of the compound that needs extra atoms. Coefficients are applied just like distributing property in math through all the symbols in that formula. Again, this coefficient applies to all atoms in the formula. As a result, you've probably screwed up one of the other atoms. Now, you're going to continue working back and forth, changing the atoms until they all balance. And it could take a while. But you know you are done when you have the same number on both sides of the equation. When the same number and types of atoms are on both sides of the equation, then you have it balanced. Now, folks, balancing will never work properly if you have the formulas wrong. So we have to make sure that we are putting the formulas down on our paper correctly. And we'll talk about this trick with our second example, but we're going to simplify the equation. And again, like I said, we'll talk about that more here in a few minutes. Now, we have an example from our book for balancing a chemical equation. This example shows us the synthesis of water from hydrogen and oxygen. So we have H2 plus O2 reacts to produce H2O. And our first step is to count the atoms. Now, on the left-hand side, we have 2 hydrogens, 2 oxygens. And on the right, we have 2 hydrogens and 1 oxygen. You can see that the number of red spheres is not the same on the right side as it is on the left. So we're going to add a coefficient of 2 in front of water. Now, this means that we have 2 water molecules. Now, what that does is it changes the count of atoms. So now we have 4 hydrogens and 2 oxygens. We fixed our oxygens, but our hydrogens now are not in balance. We're going to fix this situation by putting a 2 in front of the H2. So now we have 4 hydrogens, we have 2 oxygens on the left, and we have 4 hydrogens and 2 oxygens on the right. So our balanced chemical equation is 2H2 plus O2 react to produce 2H2O. Our first balancing example shows us hydrochloric acid plus calcium hydroxide reacts to produce water and calcium chloride. HCl plus CaOH2 react to produce H2O plus CaCl2. My first step again is to count the total number of atoms on both sides of the equation. As difficult as this equation looks, we only have 4 atoms to worry about. And on the left-hand side of the equation, I have 3 hydrogens, which I get by multiplying this 2 through the parentheses and then adding it to my hydrogen from HCl. So I have 1 plus 2 equals 3. I have 1 chlorine, 2 oxygens, which again comes from the 2 behind the parentheses, and I have 1 calcium. On the right-hand side, I have 2 hydrogens, I have 2 chlorines, and then I have 1 each of calcium and oxygen. Now you can see from the left and the right that our hydrogen equals 3 and this hydrogen equals 2. Obviously, our equation is not balanced. Now I'm going to pick the thing that's easiest for me to rectify. So I have 2 oxygens on the left and I have 2 oxygens on the right. So I want to put a 2 in front of H2O to make my oxygens equal 2 on the product side. Now at the same time as I've fixed my oxygens, I've also screwed up my hydrogens, because now I have 2 times 2 equals 4 hydrogens. And again, my hydrogens over on the left hand side equal 3. Now keep in mind that I have 2 hydrogens here in calcium hydroxide. I can rectify the imbalance of hydrogens by putting a 2 in front of HCl. When I put a 2 there, now I have 2 H's plus the 2 H's from calcium hydroxide gives me a total of 4, which is the same number as on the right. Because I've fixed my hydrogens, I've also then added another chlorine. Before I had 1, now I have 2. So if I look at the left and the right, my numbers are the same all the way across. This equation is now balanced and represents the law of conservation of mass. So this equation reads 2 hydrochloric acids plus calcium hydroxide react to produce 2 water and calcium chloride. Our second example is much more complex. What this says is ammonium carbonate plus lithium phosphate react to produce lithium carbonate plus ammonium phosphate. This is a simple double replacement reaction. And if you don't know what double replacement reaction means, that's fine. We'll learn about that in the next PowerPoint. But this appears to be tricky. I can make this equation simpler by combining terms and putting in my own variables. You'll see here that NH4 is in green, just like it is on the right hand side of the equation. Because NH4 is the same on the left as it is on the right, I'm going to call NH4 X. And I'm going to do the same thing for CO3. I have CO3 on the left and CO3 on the right. I'm going to call that Y. And Z is going to equal PO4. I have PO4 on the left and I have PO4 on the right. Rather than going through and balancing out the nitrogens and the hydrogens and the carbons and the oxygens and the phosphorus, it's easier for me to simplify this, and it makes this process a lot easier. Now I can rewrite this equation as X2Y plus Li3Z react to produce Li2Y plus X3Z. So let's take a closer look at this new simplified equation. Again, I'm going to count up the total number of X's and the total number of Y's and the total number of Li's and the total number of Z's on both sides of the equation. And I can see that I have 2 X's, 1 Y, 1 Z, and 3 Li's. On the left, I have 3 X, 1 Y, 1 Z, and 2 Li's on the right. Now, obviously this is not balanced. I have 2 X's on the left and 3 on the right. Now, the simplest thing for me to do in this situation is to find out what the least common multiple is between the 3 and the 2. And the least common multiple is 6. So I'm going to change my lithiums to 6. And by doing that, I create 6 lithiums with a coefficient of 3 in front of the Li2Y. So here I have 3 Li2Y, which gives me 6 lithiums, and now I have 3 Ys. Well, over on the left, I only have 1 Y. So I want to fix that by giving myself, I'm sorry, we're going to change lithiums now to 6 as well. So I can put a 2 in front of Li3Z, which gives me 6 lithiums, and now it gives me 2 Z's. So now I have 2, 1, 2, 6. I have 3, 3, 1, 6. Now obviously I need to fix that situation. So I'm going to put a 2 in front of the X3Z, which gives me 6 X's. Again, the least common multiple between 3 and 2 is a 6. And in effect, I also then change it to 2 Z's. So now my Z's are balanced, my lithiums are balanced. On the left-hand side of the equation, I'm going to put a 3 in front of X2Y, which gives me 6 X's and 3 Y's. So all of my numbers are the same, left and right, on both sides of the equation. So my equation now is balanced. 3x2y plus 2li3z react to produce 3li2y plus 2x3z. Now, unfortunately, I can't simply leave it like this. I have to go back in and put my variables in for these different terms. My finished equation is 3NH4 2CO3 plus 2Li3PO4 react to produce 3Li2CO3 plus 2NH4 3PO4.